Okay, so we're finishing up the sort of the heat of reaction type thinking for thermochemistry, chapter 5. We did heat of formation last time, and then we tabulated, we made tables of heat of formation for all these different compounds. What was required before we could put it in a table? This is really today's main point. We're going to hit this 2 or 3 different ways. So before I could put a table together of heat of formation values, what did I need? And I use the analogy of altitude. What did I need for altitude? If I was going to list the altitude of what?
Sea level?
Yeah, sea level was the reference state. But you're right. The elements in their standard states is the reference state. That's the sea level idea for heat of formation. So if it's 0 to form the elements, because that's what nature gives us, then everything can be tabulated, meaning put in a table relative to the elements. So we looked at acetylene was above, it had a positive enthalpy of formation, which meant the elements were here, and acetylene was actually uphill thermodynamically from the elements. So you could conceivably like poke acetylene and have it break down into carbon and hydrogen and release energy. And that's what we use. There's a really good one. What is it called? Sodium azide, I think. Sodium azide is way up here thermodynamically from sodium metal and nitrogen gas. Nitrogen gas, super stable gas. And so I think that's the compound in your airbags. So you've got this solid in a little can, looks like a little tuna fish can, inside your steering wheel, and you hit something, and inert, like these little pendula weights in your front of your car slam forward and complete the circuit. And again, they don't just slam forward when you bump into something. You got to hit it pretty hard. So they slam forward when you hit something hard, creates electrical circuit, sparks the sodium azide, and it decomposes and goes down to its elements of nitrogen gas and sodium metal. Now it's pretty hot, so it can burn you, but getting a little burn on your arms from the vented hot gas is way better than crashing into the steering wheel or the windshield. So it produces a lot of gas really fast, fills up the airbag, and actually it has to fill the airbag completely, and then these vents pop out on the side, and it starts to deflate before your face hits it. Because that would really be bad if your face is still coming forward and the airbag's still filling up. So it wouldn't be like hitting something. You would be hitting something that's also hitting you back. Like it'd be like leaning into a punch. You're going to hit me in the face. Let me lean into it when you swing. Okay, that'd be bad. And so you have to, it's all timed perfectly. The airbag fills up and starts to soften when you hit it. And all of that technology goes into it. And it's, again, thermodynamics is what's driving that. Little spark, sodium azide, drops down in energy, produces a lot of gas that expands and fills up the airbags. So let's look at the Alex reports. Good job on 7 folks. Finish this one that's due tonight. We got a couple people that are halfway done, so keep it up. Okay, so today's topics, we really only have 2 topics. It should go pretty quick, but on the Alex report, it says only 10% of the people are ready to learn this. And so I don't know what Alex uses to complete that, but that's why we're working on this. I'm trying to get you guys ready to complete this tonight in an easy manner. And these are pretty easy. Let's first start with the energy units. So energy units are kind of crazy because we've been dealing with energy for centuries. So it goes back to calories, and now we have the SI unit of joules. We're not even talking about it, but there's another energy unit called a erg. And erg, you've heard of ergonomics. Again, that's using the energy unit in that word erg. So let's look at calories. So a calorie is a unit of heat or other energy. It's the amount of energy needed to raise 1 gram of water by 1 degree Celsius. So the Celsius scale is based on water. It's 0 where water freezes. It's 100 where water boils. And then the unit of energy of a calorie is take 1 gram of water and move it 1 degree on that 100 degree scale, and that's 1 calorie. So everything kind of based on water in the old system of units. Now the SI system of units, where we get into all of the, kilogram, meter squared per second squared, using the metric system and so on, they came up with a joule as a unit of energy. And so this is the definition of a joule, of a calorie, 4.184 joules. So we could use that equality to convert from joules to calories and so on. Now, of course, that's a small amount of energy, so we're probably going to be dealing in thousands of those things. And so it's really common to talk about kilocalories. But this is where it can be confusing, because 1,000 calories is a kilocalorie, but it's also 1 cal with a capital C. So that's a nutritional calorie. And so I'm sorry, but it's case sensitive. This is the only time I think a unit. Now our prefixes are, let's see, which ones? There are certain things that are case sensitive, like a capital M was mega and a lowercase m is a meter, so a capital G is giga, lowercase g is gram. But this one is weird because they're both energy units. So a lowercase c is a calorie, and a capital C, CAL, is also a calorie, but they're a factor of 1,000 different. So a nutritional calorie is 1,000 lowercase c calories. I didn't come up with this. Don't blame me. Okay. But so here's some conversions. Lowercase c cal is 4.184 joules. A kilocalorie is 4.184 kilojoules. So you put a kilo on top and bottom. That's totally legal. You have 1,000 lowercase c calories in a kilocalorie. Okay. Or you could have a capital C cal over a kilocalorie. Those would be the same. So let's use some of these. Some of the ALEKS problems are just converting units of energy. So, but before they do that, I just can't help myself. Whenever we're dealing with calories and so on, this is your everyday life. You look on the nutrition facts on the back of a bottle, and that's what you're going to see. Like here's peanut butter, 190 calories, capital C, nutritional calorie. Okay. And so we could figure out, we've got 190 calories. Well, that's, a kilocalorie per calorie, 4.185 kilojoules per kilocalorie. So this is 795 kilojoules. And so then we could go and look like comparable things on the enthalpy of combustion tables or formation tables. We could sort of put peanut butter on that table and kind of show some things about that. And so this, just knowing this is the piece right here that you would need to know to kind of get it over to joules. You need to know that it's 1 capital C calorie is 1,000 lowercase c calories. Okay, so converting energy units. These are the problems that you have in ALEKS. It's going to be hard for y'all to see in the back because I've got all 3, squares here, and so the conversion factors are going to be kind of small. But let's go ahead and work through some of the math. So this one's pretty easy here. We've got a calorie. This is kilocalorie. Remember, kilo is 10 to the 3. Okay, and so this is 10 to the 4. And so if we take 3 away from that 4, I have 7.5 times 10, right? Or 75 kilocalories. Okay. I could take that and I could multiply that by the 4.184 kilojoules per kilocalorie, and then I could get the 314 kilojoules. So that's pretty straightforward, just following the units. Again, this is lowercase cal, this is lowercase cal. So those cancel, and I've got kilocalories. Then kilocalories cancel, and I've got kilojoules. So just follow the units. Here we've got a number of kilocalories, so we're going to go over here to calories. So 405, again, following the units, there's 1,000 calories in a kilocalorie. And so it'd be 405 times 10 to the 3, or 4.05 times 10 to the 5. So again, in order to keep track of the significant figures, it would be really hard to write this as 40500. Let's see. Oh, right. Yeah. Because how do I write that and let everybody know I only have 3 significant figures? I can't put a decimal place here. If I put a decimal place there, then I'm telling everybody that I have 6 significant figures. So I cannot do that. So I've got to write this in scientific notation in order to communicate that I only have 3 significant figures. So that's sort of an added complication to these problems. It'd be nice to just be able to write 405,000 and get it right, but it's going to fuss at you because it's going to say, well, you didn't do the significant figures. So you got to write it in scientific notation sometimes to communicate that you only have 3 significant figures. Okay, this one here is pretty straightforward. This is kilocalories, so they're going to cancel to get to kilojoules. So again, 1.69 times 10 to the 3 kilojoules. Another example where it would be impossible to communicate the significant figures. If I wanted to write 1690, I could not communicate that those were my significant figures and that 0 is extra. Okay, so then that's the last one. We've got 920. I've got to just divide that by the 4.184 kilojoules to get the kilocalories. So that's 220 kilocalories. Now, that's, again, I start with 3 significant figures. I'm going to end with 3, and I can put a decimal place there to indicate that I have 3 significant figures. And then this last one, I've got 920 kilojoules. And I can just do, instead of a kcal there, I can just put 1,000 calories. Now this one I'm going to have to write in scientific notation because I got 920 times 10 to the 3rd. So I'm going to switch that to 2.20 times 10 to the 5th. So again, I've got to communicate that I have 3 significant figures. So that's this type of the ALEKS module. This is this type of problem. And so just follow the units. It's just drilling you on converting from one kind of unit to another. So use the units to determine whether you need to divide by 4.184 or multiply by 4.184. So that's the only trick, is just using the units. If you don't put units in your fractions, like if you want to look at this and you say, well, I'm going to go 75 times 4.184 equals 3.314. Okay, that's great. That's the math. But the units would tell me if I'm making a mistake or not. Because down here, when I'm going this way, I need to divide by 4.184. But I don't necessarily know that if I don't follow the units. If I show the units in my conversion, then I can see that the kilojoules have canceled if I'm dividing by 4.184. Okay, so let's look at the enthalpy of formation table to kind of prepare for this next set of ALEKS problems. Remember we just talked about the reference point is elements in their standard states at room temperature in 1 atmosphere. That is sea level for this table. So that's where we would put 0. So we could have on an energy level diagram at 0 energy, we could have a line that shows all of the elements in the periodic table in their standard states. And then we could put a line for every other compound in nature, and it would be relative to that 0 level. Some would be below sea level, and others would be above sea level. If sea level, we mean by our reference state. Okay. So there's one problem, though. For this table to be universal, we have to measure the enthalpy of formation for every compound. And we have to do it 3 times because we want to do the solid, we want to do the liquid, and we want to do the gas. So just like water, there's ice, there's water, liquid water, and then there's steam, liquid vapor. So we would have a different entry for water, S, L, and G. So we have 3 entries for water, 3 entries for every other substance in nature. So this table is going to get big fast. Think of all the compounds. It's just unruly to try to make a table for every known compound. I mean, we have thousands upon thousands of compounds that have been determined, so it is a big table, but it's not universal. So here's our here's our current situation. So if we're going to look at the formation of water, we have our sea level there, the C0 kilojoules for the elements in their standard states, hydrogen and oxygen. Okay, and we can form water, and we see that that's minus 484 to form 2 moles of water. Okay, so we would say it's sort of downhill from the elements, a very stable compound. Okay, what if we did this a different way? What if we broke the oxygen apart? And we would pay a penalty to do that. We would be breaking a double bond. We'll learn about double bonds and single bonds later. But we would break this really stable bond between the 2 oxygen molecules, and we would pay a penalty. So we're going uphill, so we got to put in energy. We got to pay our way, right? So that's going uphill 498 kilojoules. And then we've got 2 moles of hydrogen molecules, and so we would break one of those HH bonds, and that would cost us 436 kilojoules. We got another hydrogen molecule. We got to break it apart. And so then that would also cost another 436 kilojoules. So we could look at the bond energies of our elements and break them apart. So we break apart the oxygen, set those atoms here, break apart the hydrogen, set those there, break apart the hydrogen, set those there. So now we've got 6 atoms. And we've had to pay to get those 6 atoms, but up at the top, we got 4 now. On the table, we have 4 independent hydrogen atoms and 2 independent oxygen atoms. And then we can make water. So when we break those bonds, we go uphill, so we add those bond energy values. And then we can start making our waters. So we take a hydrogen and oxygen, click it onto an oxygen. Okay, hydrogen, click it to an oxygen, and we get some energy back. We get 363 kilojoules. And then we can take the other hydrogen and stick it on that oxygen. We've made 1 water molecule. And we get another 463 kilojoules. And then we can take the other hydrogen and oxygen, snap them together. We get another 463 kilojoules for that bond. And then we could make the last hydrogen, stick it to the OH, and we make the last water, and we get 463 kilojoules. So this is just a different way. We started the elements, we went uphill and then downhill and formed water. And this is kind of like Hess's law, right? You can go any way up and down on this as long as you end up where you want to be. You can break bonds, make bonds, and so on. So when we make those bonds, we're going downhill, so we subtract those bond energy values because we're getting that energy out of the system. Okay. Conceptually, yeah, go ahead. Oh, yeah, sure. Yes, sir. All right. I'll get you one here. All right, so any questions about this concept? Okay. All right, so you'll see the power of this. Yes. Yeah, so if we're breaking those bonds, we're going to add up those values. And then when we're making the bonds, we're going to subtract them. Yeah, and so that's where we're headed for that problem, yeah. So here we broke 2 H bonds. So there's the 463 from this table. It's 2 of those. And we break an O2. And so that's the 498. And then we make the 4 OH bonds to make the 2 waters. And so that's 463 for each of those bonds, and there's 4 of them in 2 water molecules. I think the place where we mess up is we forget there's 2 water molecules. And so we would just have 2 here instead of 4. There's really 4 OH bonds in the 2 water molecules. So, but let's think about this for a little bit, and that gets us our 482 kilojoules. Okay, what if we looked at this and we said, wait a second, look up there at the top, all single atoms. If we made that our 0, so if that's sea level, then all compounds are downhill, even acetylene. Because I have 2 carbon atoms, 2 hydrogen atoms, I can bring them together. The carbons make a triple bond, the hydrogens make CH bonds, and that's going to drop down. And so this would mean that we could calculate the energy of the heat of reaction for making the hydrogen gas and the oxygen gas. This would be also the energy we get for making the water. And this situation is very similar to the enthalpy of formations because we would take products minus reactants. So the product would be the minus 1852 kilojoules relative to the atoms pulled far apart. And the reactants would be the 1370 related to the atoms pulled far apart. And so products minus reactants minus a negative becomes a positive. So you do this math and you get the same thing, 482. So this is the I would say another way to do that problem is to calculate the energy for the products and the energy for the reactants and take the difference. Mathematically, it's going to be the same. Okay, and you can prove that to yourself by doing it both ways. But this is actually the better way to think about it in terms of being able to produce the energy for the products, energy for the reactants, and take the difference. Okay, now here's our table from Alex. So if you go into the data section on Alex, it says bond energies. You click on it, and you can scroll down. It's a long set of tables, but here they are. Now that looks like a lot of information, okay, but it's really not. Compare this to the universal enthalpy of formation table. Like if we were to try to make a universal enthalpy of formation table, it'd be thousands upon thousands of compounds, solid, liquid, gas for each one of them. Whereas if you look at this, think about the millions of compounds you could make with this simple little table. Because it's got a CH bond, and you can make all kinds of molecules with multiple CH bonds. And it's got a CC bond, so you can bond as many carbons together as you want. You want to make hexane, you make 5 of those bonds. You want to make octane, you make 7 of those bonds. Put hydrogens all around them. You can calculate all of those, and you don't even need to go find the enthalpy for those individual compounds. You could calculate it by just knowing how it's bonded together. So that's why this is called a structure-based approach, because we're looking at the molecule structure and we're building it up, and we're saying, how much energy do I get from a CH bond? I've got 7 of those, so I'm going to add 7 of those energy units. How much do I get from a CC bond? I got 5 of those, so I'm going to add up 5 of those. And so I can calculate the energy for my products and the energy for my reactants, take the difference, and get my heats of reaction. So this is structure-based properties. Do you understand the difference? The enthalpy of formation really doesn't have anything to do with structure at all. It's just an experimental result that tells you how much heat was produced when you form this compound. This is more theory-based because it may not be exactly right, but it's going to be close. Okay, so a carbon-hydrogen bond, we've got one entry in this table, but is it the same if that carbon-hydrogen bond is hooked to a carbon that has a triple bond, or it's hooked to a carbon that has a double bond, or hooks to a carbon that has a single bond to another carbon? Those CH bonds might have slightly different energy. And so there's going to be some secondary and tertiary effects of the structure, but for what we call a first order approximation of our thermodynamics, this table will get it done. So Alex is just teaching you how to use this structure-based properties. So here's the problem, an example problem in Alex. So use the appropriate bond energies from those tables, calculate the heat of reaction for the following reaction. So we got the combustion of methane. So we got a methane molecule, 2 oxygen molecules making CO2 and 2 waters. Okay. So I went ahead and put this on my energy level diagram. So here I have the reactants going up to the elements, the atoms. So I've got to break 4 CH bonds, and I've got to break a couple of oxygen bonds. So see, I'm breaking those. I'm going uphill in those values. So I've got 4 CHs, which is 413 kilojoules, and 2 oxygen double bonds, which is 498 apiece. And so that's going to go up, and then I'm going to come down and make those. I'm going to make 4 OH bonds because that's the 2 waters. And so we're showing you the structure so that you know which bonds to look up. Let's find them in the table. Okay, so this HC here, I'm looking at this. This is a CH bond right there. So I come over here and I find the HC, and that's where the 413 came from. And here's the OO, Where does that come from? Well, here's the oxygen molecule, so it's showing you the structure. And so then I've got this one. So O2, 498. So that's where we're getting the numbers. And then I'm making some OHs. I'm making 4 of those. So this is what we're talking about right here. You go find them in the table. Here's OH, 463. So that's where this number came from. And now this one is, again, I talked about some finer points. You know, it might make a difference whether it's a carbon double bonded to an oxygen in another organic molecule like acetone, the fingernail polish remover, or is this double bond part of CO2? So this one has 2 entries, right? It's got O double bonded to carbon or O double bonded to carbon in the special case of CO2. Okay, and it's substantially different. Okay, and so we're going to use this one because we're making CO2. So this is the carbon double bond to oxygen in CO2. That's 799. So if you use the wrong one, you're going to get the wrong number, and you get the wrong answer. And there's 2 of those because CO2 has 2 of those bonds. All right, so this is the full thing. You got these are the bonds that you're breaking, and oh, I thought I put it next to it. These are you're breaking these, so they're positive, and we're making these so they're negative. And look at the arrows. See, we're going up here like that, so we're going uphill there. We're going downhill there. These bond energies, if you break a bond, you're going uphill, so it's a positive energy value, and if you're making the bonds, you're going downhill, so it's a negative energy value. But the table just shows positive numbers. Okay, so you got to know when it's positive, when it's negative.
And makes are always going to be on the product side.
Yeah, because you're making the products. Mm-hmm. It's the trouble that you might run into is that you may be saying, well, I thought we took the products minus the reactants, right? Because we typically subtract the reactants. So this seems backwards. But the reason it seems backwards is because we're starting at the reactants and we're going uphill to the atoms and downhill to the products. So it's the path that we're taking that makes it seem backwards. Okay.
On the making side, on the product side, how did we get the -4 for CO2 and the 2 for the...
They're swapped. This is the water. So this one is the 463 is for the water, and this is for the CO2. So it's the number of bonds. So since there's 2 waters, but there's 2 bonds in each, so that's where the 4 came from. So the 463 is this OH. So
no, where it's -4 times 463. Where do we get the -4?
Yeah, the negative comes because we're making them. We're going, this down arrow gives us the negative. Okay, and then the 4, we have 2 waters, and each water is 2 bonds.
Okay.
So there's 4 OH bonds. Yeah, so I'm going to just get rid of this 2 and draw another oxygen. Right, so now you see all 4 OH bonds. And so each one of those, when we form them, gives us 463 amounts of energy. Yeah, yeah.
And then there's the O equals C equals O. There's 2 bonds there.
Yes, yeah. And so that equal sign is a double bond. And we don't know what that means yet. We haven't done Lewis dot structures. But when we get to Lewis dot structures, it'll start to form double bonds in order to make a noble gas configuration, an octet rule. Yeah. Yes.
So on the breaking side, those are going to be positive?
Yeah, so from the table we add those on the breaking side, and then we subtract the ones we're making. And in this case, adding and subtracting shouldn't be thought of as getting rid of the bonds, because it sounds like if you're subtracting something, you're taking it away. But no, think of it as uphill and downhill. So if we're breaking those bonds, we're going uphill. So we need to go higher in energy. And then when we make the bonds, we get energy back. So we're going downhill, and so we subtract that energy. And then if the overall difference is negative, like 802, then this reaction was exothermic. It went downhill and released energy. So the positive and negative signs on energy are related to what we define as the system. So the chemical reaction is the system. Did heat leave the system? If it's negative, it left. So when this reaction goes from reactants to products, heat left the system. And so from the perspective of the chemicals, they're missing some heat. It went away. Okay. And we use that to cook our food and to heat our houses and so on, to drive our cars. Okay. So we want exothermic reactions if we want to do work with them. Okay. But so what subtracting is good. We're making those bonds and we're getting heat out of the system. So if it's leaving, that's what the minus sign is for. Okay, let's do another one. This is just forming water, but it's an Alex example. So 2 hydrogens and an oxygen and 2 waters. Okay, so here's our table. And here I don't think I did this one with the big. Yeah, I just did this one straight away, so you don't have to draw the big diagram that I was doing. But here we've got the break is plus and the minus is make, and so we've got two HHs. So that's the 436. And we got 1 double O, and we're going to make 4 OHs, and those are the 463. So these are the 3 numbers that we have. And so we're going to have 2 plus 2 times the 436, plus 1 times the 498, minus 4 times the 463s. And so this is really all you need to do for this type of problem in Alex, is just to use the table. But I show you the diagram to emphasize we're going uphill and then downhill. Yes. That help? Okay. So these shouldn't be tough, these problems, now that you know what we're doing. Okay. But think about that. With the bond energy table, this is fantastic. I can make all kinds of compounds with a very simple table. I mean, you can put that in your wallet. Not that you would, but sitting around, you're bored at a party, pull out your little table and start making some molecules, calculating their energy. If you do that, come and talk to me. Okay. I need a researcher. Yeah, that's great. Okay, now I spent some time here. This is enrichment. You're not going to need to do this. Okay, but this is looking ahead to let's say we didn't have even the bond energy for a molecule. So it's a bond energy that's not in the table. Now what? Well, this is how it's really done. We use computational chemistry, okay? And this goes back to, let's see, what slide is this? This is 18. Okay, let's go home. Well, in just a minute. So I use this software called Gaussian, and you're able to build the molecules. And so here's the little window. I've got selected a water type molecule, and I click in this blue screen, and it gives me a water molecule. Or like I could pick carbon out of the little list, and it would have carbon, and I could pick a carbon that's bonded to 4 things, and I click over here in the window, and it gives me a methane molecule. And if I clicked on one of those hydrogens, it would bond the 2 carbons together, and I could start making bigger and bigger molecules. It's a really fun program. We have a site license, so if you're curious about that, you can use the software if you want. Make oxygen with the double bond. I could make CO2 with the double bonds, and so on. And I could calculate, here's the thing, I could calculate the energies of those molecules. So instead of using a lookup table of bond strengths or the enthalpy of formation tables, this is actually calculating the energy of the molecules. So it's limited only by my imagination. I could build all kinds of new molecules with this software and calculate their energies. Now look at these energies. Negative 394,482 kilojoules. So this is 394 megajoules. It's a hugely negative energy. So something tells me this doesn't have the same reference state as the elements in their standard states or even free atoms, and it doesn't. So this is the actual reference state for computational chemistry. So all nuclei and electrons fully separated. So think about how much that takes. I'm taking the oxygen atom and I'm pulling all 8 electrons off of it. So I just have an oxygen nucleus and 8 electrons separated infinite distance from each other. So there's no drop in energy. That's as high, that's like, instead of sea level, that's Mount Everest. And so if you think about if Mount Everest was 0, then every point on Earth would be negative. And so that's what we've done. We've picked the highest possible energy state of nuclei and electrons fully split apart. So now I can calculate the energy of every atom and every molecule that I can make, and they're all negative. Okay, and then we do the delta, the products minus reactants, and so here's the energy for my 4 atoms. I'm sorry, for my 4 molecules, and so we can calculate this energy here. It's 1 mole of the methane and 2 moles of the oxygen, and here's my energy for my reactants. And then I could take the products, and I have 1 mole of the CO2 and 2 moles of the water, and here's my products energy. I've got those marked here on this landscape energy axis, and I could take the difference between those two, and I could get my 802 kilojoules for the heat of reaction. So it's just another way to do it, but this is great because it's all on the computer. I don't even need a table. So I can just pull up my computer, build my molecules, calculate their energies, and then I can start doing my thermochemistry and determining. So this is how it's really done. Like in Dr. Gross's lab, and a lot of the organic chemists use this. They'll propose a synthesis and they'll model it and they'll see if it is even feasible before they go to the lab. And so they'll do a lot of their work. They call it, you've heard of in vitro, right? In glass. You've heard of in vivo, in life, in human. This is called in silico. It's in the silicon, it's in the computer. I think it's a silly thing, but that's what they call it, in silico modeling. And so this is computational chemistry. It's something you can play with. We have a site license for the Gaussian software. So if that's something you're interested in, shoot me an email, and I'll let you play around with it. If nothing else, it's fun to build the molecules. In fact, we've got some time. This is such an easy Alex set, so let's just play around with the Gaussian, if you don't mind, if that interests you. So let me pull it up. And let's see, let's do display capture. Yeah, there we go. And Gaussian, let's move it over here. Yeah, here we go. All right, so here we have, make sure it's not maximized. And this one. Okay, so what do y'all want to make? Nitrate. Okay, very good. So let me maximize this over here so I can see what I'm doing. All right, so nitrate. So up here we have this. Why is it not coming up? Oh, okay. Why isn't it behaving? Supposed to get some options when I click that button, and something's not working with the double screen. Let me see. Oh, it's showing up over here. So it's spawning all my new dialog boxes over on my laptop screen. So here we are. So we got nitrogen, and we got all these different types of nitrogen. Okay. And so let's pick this one. Well, no. Let's do a nitrogen atom. So we click there, and then we want to add. It's bonded to 3 things, right? So we want to come up here and we want to add valence. Where is it? No. That's delete. Yeah, add valence. Okay, here we go. So we're going to click that. All right, so it's got 3 things that I can bond onto it, and I'm going to put oxygen atoms on those. Okay, so I'm going to come over here, and I'm going to pick my periodic table again, and I'm going to click on this, and I'm going to pick oxygen. Okay, and I'm going to pick an oxygen atom, and I'm going to come over here and click those open spots. So it puts hydrogens on it by default, and so there's my nitrate. And I can zoom in, and so there's nitrate. And then I can come up here and I can calculate. I can tell it all kinds of things to calculate, and it will ask for all these different options about the model to use. And so this is using the computational models that are built in to determine the geometry of it, the energy of it, and all of those kinds of things. Okay, let's pick something a little bit more, a little different. So let's come up here and clear this. I don't see it clear. Yes. Okay, so let's come over here and look at the rings and things. We've got a ring template. But sometimes rings are hard to build. So, I don't know, let's pick something interesting, like cyclohexane. Okay. So there's cyclohexane. We can go back to that ring fragment and pick some other little cool piece to put on there. Let's put one of these little cubane things on there. So there. So you can build pretty complex molecules very quickly. We can add all kinds of functional groups on there. Let's put an acid group on there. So yeah, here's a carboxylic acid group. So let's make this molecule have a whole bunch of acid groups on it. And so there's the little proton that comes off. When this goes into solution, it can donate that proton and it can act like an acid. So this is Gaussian, and it's a good software that you can use to model the different compounds, their thermodynamics. We can also model their spectroscopy and learn all about them, so the reactivity and so on. So this is sort of a foreshadowing. If you go on into chemistry, this is an avenue of chemistry that's not in the lab. So let's say you just love computers, you love programming, you like chemistry, you don't really want to be in the lab, you know, elbow deep in all the solvents and everything, and it's also real smelly. I hated the smell of organic chemistry, and so I decided to go physical chemistry, and I love it. You know, so there's other options than just being in the lab mixing up solutions. I do that too, but I do more of this. All right, y'all have a good day.